говорите все время в микрофон для обратной связи. Трансляция уже пошла.
Открыто, открыто, открыто.
Можно начинать. Пресеты. Первый это вот, да, третий на нас, четвертый, пятый, 4-5 зал. Сейчас,
Рикардо.
Да. Hello.
Добрый день.
Доброй ночи.
Ты готов?
Yes, yes.
Прекрасно.
Первый.
Ну, тогда начинаем. Добрый день, коллеги. Начинаем мастер-класс. Рикардо Волс. Прошу любить и жаловать. Канада. Глубокая ночь. Человек вот подготовился, чтобы провести у нас мастер-класс. Рикардо.
Да.
Рикардо, тебе
Hello.
слово. Кинь.
Доброй ночи.
Ты готов?
Yes, yes.
Прекрасно.
Первый.
Ну, тогда начинаем. Добрый день, коллеги. Начинаем мастер-класс. Рикардо Волс. Прошу любить и жаловать. Канада. Глубокая ночь. Человек вот подготовился, чтобы... Начинаем.
Okay.
Let's go. Андрей, у тебя звук выключен. Включайся. Андрей. Ага, все, включено. Поехали. Рикардо, поехали. Let's go.
Okay, let me share my screen. So, good morning to you all. Thank you for coming. And I'm very excited every time I talk about this subject because it was a big discovery for me, and I hope that it will be a big discovery for you too. And the subject is why and how should geologists use compositional data analysis? And this is a true story that I will tell you how everything happened. So for those who don't know me, my name is Ricardo Valls. I graduated from the best university in the world, MGRI, in 1983. And I'm also a PGO in Ontario and a qualified person. I am also the author of several books on QA/QC, geomathematical modeling, the use of artificial intelligence. And in today's conference, we will be talking about specifically this book here. You have the link right here. And this book can be bought directly from Amazon.com. And we are even exploring the possibility of translating this material into Russian to have a Russian book. So this story started for me in the year 2004. I was visiting Florence for the 32nd International Geological Congress. Beautiful city where it was a wonderful conference, 5 days. And on the last day, I was walking, giving a last walk through the rooms, and I wandered into a classroom that said compositional data analysis. And I asked myself, what is that? Because I have been studying statistics since I graduated in 1983. And I love geomathematical modeling. I got wonderful professors at MGRI, and I never heard this subject. So I entered and, you know, start listening to everything that they were talking about, blah, blah, blah. And at some moment, I asked them, you know, you're talking about statistics, the simplex, this and that. I haven't heard you say the word correlation. Why don't you speak about correlation? And I swear to you, it was like I was an alien that just came out from a saucer. Everybody look at me and say, what are you talking about? There is not such thing as correlation. Correlation do not exist. So of course we start discussing, blah, blah, blah. This was in 2004. And they invited me to say, you know, if you want to know more about compositional data analysis and why correlation don't work, you need to come to Girona, that's in Spain. They have every 2 years, they have a congress called the CODA work, and you will understand better. So next year, I went to Girona, and it was a wonderful conference. I want to show this little old man here. That is Dr. John Atkinson, who died regrettably in the 23rd of December of 2016. He was a Scottish statistician, and he is the author, the inspiration for everything you're going to be hearing today. So again, I was discussing with them about correlation because as a geologist and as a geochemist, all my life I use correlations, and with relatively good success. So it was a big surprise for me, and I am sure it's going to be a big surprise for you when they explain me that even Carl Pearson, the creator of the Pearson correlation, wrote in his book in the time when he presented his paper on correlation that his method will not work in the case of closed data. And what is closed data? Closed data is any kind of data that is estimated over the basis of a fixed volume, like part per million, percentage, day of the week, etc. And if you don't believe me, you can really go to this link here. This is the paper of Pearson, where he wrote, the paper is called On a Form of Spurious Correlation That Can Arise When Indices Are Used in Organ Measurement. It was on biology, but it is useful for geology too. So that was for me a big, big surprise. So what they were saying to me is that correlation, regression, even statistic, I was doing it wrong. So I need to stop. I need to learn this new thing. And I hope that you will stop to understand this new method, the compositional data analysis. And if there is one message that I would love you to take from this presentation is that you cannot do correlation analysis on closed data as the geochemical data. You cannot do it, okay? But now I will show you why. This was 2005. As I mentioned, they have this conference every 2 years. So for 2 years, I was preparing myself because I really could not believe what they were telling me. Even after I read that Pearson itself said that no correlations will not work with geochemical data, I could not believe it. I mean, so I had an idea. I will create a model. So once and for all, I will prove that my statistic works. And the model that I created, it was like a model of a deposit of a copper mineralization associated with a tectonic zone in a tonalitic intrusive. And how I did create this, I generated a grid of data for a full, not only trace element, but also major oxides. I cover a grid that will create right here an ore body. And I said, okay, I'm gonna now use my statistic with this data, use my correlation, and I will show them that yes, correlation works. By the way, the original paper, this paper can be downloaded for free from Wikibooks, and that is the link to download the paper, okay? And next I will show you a portion of the table of data that I created. So as you see, I created a series of samples with ethene, northene, major oxide, and all the trace elements. Now, what I also did, that my model, my data, will follow a preset of conditions. First, it will be a closed system, which means that the sum of all the component of every sample will be equal or very close to 100%. The second aspect will be that there will be no null values or below the detection limits. I wanted to make this data set very simple because I only had one objective, to prove that correlations work. Third, there were no statistical outliers, okay? And then, and the most important part is that when I created my data set, I introduce correlations between certain elements. For example, as you can see in the graphic here, I introduce a positive significant correlation between copper and arsenicum, between nickel and cobalt, and magnesium and potassium, okay? And how I did that? Very simple. For example, I have the column of copper and the column of arsenicum. If I put a number that was bigger than the previous one, I would put a number that would be bigger than the previous one for arsenicum too. Okay, so if they both go up, they both go up. If it goes down, they both go down. I also created a series of negative significant correlations. So for example, here you can see the example between cobalt and copper. Again, if I increase the value of copper, I will decrease the value of cobalt. And all that I did it manually. It was a long, long task. But I created a table that I knew for a fact that contained negative and positive correlations. And according to the model, these are the two range correlation coefficient that I need to explain. I will explain later how we create this coefficient, the range correlation coefficient. But basically, if an element is in the numerator and the other one is in the denominator, that means that they have negative correlation between them. And if they are next to each other, like for example, calcium and sodium and copper and arsenicum, that means that they have positive correlations, okay? So all these elements have positive correlations, all these elements have positive correlations, and all these elements have negative correlation with all these elements. Okay, that's the basic. And as I said, I will explain you in this presentation how you can get the range correlation coefficient. So, case one, I took all my data. I didn't differentiate between major elements and trace elements. I just put it all together. And since we know that there were no hurricane values or zero values, the steps of statistical processing were first, the determination of the distribution law by the method of the asymmetry and the excess, because when I was a student, they told me many times that the correlation depends strongly on the distribution law. So you need to normalize all your data. Second, using Excel, I calculated the Pearson correlation between the different elements. And then I used the student's critical value to determine the meaningful correlations. And what do I mean here? You probably have heard the saying that you can have a correlation between the number of butterflies in South Africa and the amount of gold in Brazil. You can have correlation between anything. Correlation is just a mathematical equation that will give you value between +1 if it is positive correlation to -1 if it is negative correlation. But not all the correlations are significant. Like in the example that I mentioned before, there is absolutely no causality between the amount of butterflies and the amount of gold in Brazil, okay? That is why we use what is called the student criteria, which is this formula here that you can see. And it allows you to determine which range of your correlations are significant. That means that they are true in quotation marks. This is the formula. There are tables to determine the criteria for every correlation. But in practice, if your population is greater than 30 samples and working with the probability of 95%, which is the normal thing that we use, if the student criteria is bigger than 3, it means that the correlation is significant. And let me show you right now a section of the table of correlations, okay? And as you can see here, we only have the significant positive and negative correlations, okay? And for example, you can see here that there is a significant and negative correlation between the silica and the aluminum, the silica and the iron. There is a strong positive correlation between the copper and arsenicum. Of course, I introduced all this correlation myself, so I knew that I'm gonna get it, okay? Now, for you to understand better, I will spend a couple of slides explaining how to select the range correlation coefficient. How do we make this coefficient, which is incredibly useful in geochemical exploration? So we start by sorting all the significant correlation from the most negative to the most positive, okay? And then we start making the coefficient, putting the elements in the numerator and the element that has a negative correlation in the denominator. Okay, so we create a numerator and denominator formula. And each time one element is repeated, it has correlation with a separate element, we will put a dot or an asterisk on top of that element, as I'm showing here in this equation. So in that equation, you have copper, which has a significant positive correlation with arsenicum. Copper has a significant negative correlation with cobalt, and arsenicum have a significant negative correlation with cobalt. That is why copper and arsenic are on the numerator, cobalt is on the denominator, and because cobalt has correlation with copper and with zinc, we have the 2 dots there. So that is basically how we create our range correlation coefficient. Once we finish with all the negative, then we start with the positive one. And we then, sometimes you will find a case that you have an element that doesn't correlate. For example, we may have lead, and lead has no correlation with this element. So you create a new range correlation coefficient. But then later on, there may be another element like silica that will have correlation with lead and will have a correlation with copper. So in that case, you can combine the correlations. So basically, you usually get 1 or 2 range correlation coefficient of all your data. Okay, so let me show you an example. This is a series of data. In gray, this part here are the non-significant values. According to the criteria of students, these correlations are not significant. So we are not going to touch them. So as I said, we put all the correlations from the most negative to the most positive, okay? So which will be the first correlation pair? Well, you have gold over nickel, okay? Because gold is negative correlated to nickel. The next one will be gold again with nickel and cobalt. So because gold appears a second time, I put an asterisk on top of the gold. And of course, nickel and cobalt will have positive correlation, and both of them will have a negative correlation with gold. I continue. The next element will be copper, which will have a positive correlation with gold, and at the same time, it will have negative correlation with nickel and cobalt. Okay, and that way you continue with all your negative parameters until you finish all the negative correlations, okay? Which is right here. Now, I will give you a few seconds to think about where the positive correlations will be located. Just a couple of seconds. So now you're going to start from the bottom to the top. Gold, copper, gold, cadmium, okay? What will be the RCC that you will get at the end? Okay, so this is the RCC that we get for all the negative. So we have 3 times copper, 2 times gold, 1 times silver, divided by 3 times nickel, plus cobalt, plus lead, plus zinc. Now, I would like you to try, if you have a paper and pencil, please try to find the correlations for the positive part. I will give you 30 seconds on the clock. Okay, so this will be the final RCC, range correlation coefficient, for this example, combining all the negative and the positive. Okay, now there is a way of representing this correlation coefficient in a graphical format. I call it the dendrogram. Okay, and it would be great if you had a ruler and a compass nearby to do this exercise. I know that we did not prepare for this, but I just want to show you quickly how can you make a graphic of the correlation, and what is the importance of doing this graphic to interpret the geochemistry and the geology of your data. Okay, so what I do is very simple. Here's the same table, okay? The same table with the same correlation, etc. But we added a column. It's called the column L. And L is not from the English word length. It's from the Russian word Lyudmila. I put it in honor of my wife. Okay, and it's a very simple formula. L equals 4 plus 1 minus each correlation divided by the maximum correlation. The maximum correlation in our case is 0.99. Why 4 is after doing this millions of times. If you have a normal sheet of paper and you start making this graphic at the center, a distance of 4 centimeters is the perfect distance to make the whole graphic in one page. So we start, on the contrary, this time we start with the biggest, strongest correlation. And what you see here, I converted this L is a representation of the distance between the elements. The strongest the correlation, the shortest this distance will be. The weakest the correlation, the biggest this number will be. So we start with gold and copper, and we put them at 4 centimeters apart, and we put it with a red continuous line. The next element that we will need to put is cadmium. And we know that the cadmium is at 4.22 centimeters from the goal. So 422 from the goal, but I don't know exactly where. I need a third element. I need the correlation between the cadmium and the copper, okay, which is 424. So with a compass, and I lost here the screen, I don't know why. Just a second, please. Okay. Sorry, but we lost the screen here. But anyway, this is the important thing. So I know that the cadmium is at a distance of 422 from the gold and at a distance of 424 from the copper. So if I have a compass, I make 2 circles, and the intersection of those 2 circles will give me the location for the cadmium. Okay, and because all of them has positive correlation, I put red lines between them. The next case will be nickel, and nickel will have a negative correlation with gold and a negative correlation with copper. So I do my 2 circles where they intersect. That will be the position of nickel, and because they are negative correlation, I make the line in blue and not continuous. Then I position cobalt. Cobalt, I know that is 4.56 centimeters from the nickel and 580 from the gold. Again, I do my circles with the compass where they intersect. That will be the position of the cobalt. And as you notice, cobalt and nickel has a positive correlation between them. That is why you have the red line. And you continue doing this graphic until you finish all your elements. And why do I say this is such an interesting method to do? As you can see here, you have very strong correlation between gold, copper, cadmium. Cadmium is usually pyrite, means pyrite, okay? But you also have mineralization in the deposit of silver, but you can see it doesn't have correlation with the main element. This is showing you that you have 2 separate type of mineralization. One that is copper, gold related, probably in the pyrite, and you also have a separate silver mineralization, which could be related to, I don't know, a different process, etc. You also notice that the lead has no relation with the mineralization. It's a lithological element. So this is very useful to do some preliminary interpretation of the geochemistry of your data. Okay. So if our method, the normal correlation works, I should obtain these two range correlation coefficient because I did put it there. So when I apply Pearson, I got these two coefficients. And if you look closely, yes, there they are. There is the aluminum inverse correlation with the silica, and there is also the calcium, the sodium, the copper, and the arsenicum divided by magnesium, potassium, cobalt, and nickel. But see how many other correlations appear here. All these correlations are spurious, meaning they are not true. This is a mathematical artifact. This is what happened when you use your normal statistic, Pearson, Kendall, whatever correlation method that you use for data that are close in nature, you will get your correlation, but you will also get other correlation, spurious, that will mask the effectiveness of your method. For example, there is absolutely no correlation between the silica and the titanium. As you can see here, there is no correlation. And in the RCC that we obtained, it shows that there was a negative correlation. And you have the same situation for the aluminum, the iron, the scandium, the titanium, the loss on the ignition. So this is the problem, my friend, that when you use correlation with data, with closed data like your chemical data, you will get your correlation, but you will get other correlation that are not true, and that will mask the effect of the process. Now, if I make a map, okay, of the RCC1, this, oops, what happened? This is the ore body. Sorry, this is the granitoid. This is the ore body here. And this is the anomaly that I obtained when I used the best RCC that I got. If I'm going to be drilling here, yeah, I will, eventually I will get to the ore body, okay? But I will drill here. I will probably drill here. Here I will start getting into the ore body. I probably will drill here. So of 5 points of drilling, maybe 1 or 2 will fall on top of the ore body. And this is what we have all the time. That is why when you interpret your chemical data and you go into the field and you put the hole don't intersect the mineralization because the correlation analysis is not good enough. Okay. I thought, okay, maybe the problem is that I process together the trace element together with the major oxides. And everybody knows that there is a big difference between major oxides and trace elements. I'm from Cuba. I am very stubborn. So I decided, okay, I'm going to separate the major oxide from the trace element and repeat the process. And I got almost the same results. Okay, better located, better oriented. I will eventually, as I always say, I will eventually get into the mineralized zone. But look, I will also probably drill here and drill here. So let's get some preliminary conclusions or recommendations. And the conclusion is that yes, Pearson was right. When you try to apply correlation analysis, being Kendall, Will, Pearson, any correlation model, if you try to apply to data that is close in nature, you're going to get a lot of spurious correlation. And there is the possibility of separating the major from the trace, but again, is not going to give you the best result possible. So, okay, I have to accept that my statistic was not good enough, but that doesn't mean that theirs is. Well, does it? I strongly recommend you to download this program. It's called CodaPack. You can download it from here. And what CodaPack is a freeware, okay? What CodaPack does is it takes your data, which is closed, and it opens it. Once you have your data open, then you can apply any statistical method that you are used to. Remember the old man I mentioned at the beginning, Dr. Atkinson? Well, he created the statistic of the closed data. This is what is called the compositional data analysis. It's a special branch of statistics. As I said, it was discovered in 2007. It's not long ago. But these methods allows you to process closed data. And he developed a complete new branch of statistics, okay, that allows you to work directly in the simplex, and I will make the sphere so the data is closed. But it also created 3 algorithms, the ALR, CLR, and the best of the best, the ILR, to open your data. And imagine, for example, the Mercator projection of the world. Okay, the world is a sphere, and the Mercator projector allows you to put that sphere in a plane with the less amount of deformation. So in this case, I will only show you the result of after opening the data. I'm not going to explain or talk about the statistics of the simplex that is called the statistic in the sphere, which is adorable. It's one of the most interesting things that you will see in your life. It's a graphical statistics. That means that you're used to have tables and numbers. Compositional data analysis creates graphics, and you interpret this graphic. You will know which elements have correlations or not by analyzing graphics that will be created by the program. But that may be the subject of a more detailed discussion. At this moment, I will only talk about taking the data and open it, okay? And here, just put as an example, a section of the same data once we transform by using one of the algorithms. The CLR is central log ratio, it's called. And as you can see now, the sum of all the data is not 100%, it's 0, which means that the data is open. Once I have my data open, okay, then I use Excel again, and I did my Pearson correlation, and I did my RCC, and I obtained this very strange coefficient, which initially I couldn't understand. What is this? How do I got this? But again, if you look at the map, look at that. This is the 3 levels: first level of anomaly, second level of anomaly, and third level of anomaly is falling right on top of the mineralized zone. So this coefficient, these are the real, the true correlations. And most important is that there are no spurious correlations. So that is why this coefficient works so well. It's concentrated on top of the ore zone. Now, if I were to use only the strongest correlation, let's say above 0.95, plus minus 0.95, then I will get a different range correlation coefficient, and the map will be even better. I mean, this is how it's mapping my mineralized zone perfectly well. Okay. Now I mentioned that they use 3 algorithms to open the data. These ones are the CLR. The other two are the ALR or additive log ratio and the ELR or integral log ratio. And if I use the ALR, that's the coefficient, and this is the map. Again, almost a perfect coverage of the ore body. And if I use the ILR, I obtain a very simple magnesium plus potassium. And it's even better. The best result that I got is from the ILR. And ILR is the only statistical method that you could put geological information in your data before you ask the program to do the correlation. We will be, as we are trying to organize not a webinar, not a presentation. I cannot explain all this in 1 hour, but we are discussing the possibility of having a course, you know, a 2, 3, 4-day course on the full use of compositional data analysis. And I will show you there the advantage of using the ILR and why is the reason why we get such a good result when we apply the ILR. So some conclusions, preliminary conclusions and recommendations. It is very important the transformation of the data with the CODA pack, because we obtain only the true correlations, none of the spurious one. Another important point is that we can combine the oxides with the trace element, and all this data will respond to normal distributions, so they will not have statistical outliers. It simplifies the processing and make it very, very short. Now, I'm still looking for other options. What about the principal component analysis or the factor analysis? Okay. So here are two examples. On the left, you will see the factor analysis of the original data, and on the right will be the factor analysis of the ILR data. And as you can see, they both work very well. The problem with the factor analysis, principal component analysis, that you will not get one, you will get 15, 20, 30. So you need to test all of them, or you need to try to figure out which one is the one that really maps your mineralization. So who is the winner? If you want to continue to use the old way, I mean, continue to process the data as you are doing it right now, okay, do it, but only use the strongest correlation, like above 0.9. Because if you don't do that, you will get the spurious correlation mixing with your real correlations, and that will debilitate the effectiveness of your range correlation coefficient. In addition, as I mentioned, factor analysis, principal component analysis will give you a good result, but it requires from you to have a lot of information about your data. And as I mentioned, we will have, we are probably going to organize a course, and this is what I will be talking about: a brief introduction to a statistical method and geochemical survey. Again, more detail why and how we should use compositional data analysis, how to use the CODA pack, I mean, in real. We will process your own data. If you have your own data, we will process it and interpret together. And we also going to touch on graphical representation of your results. As a final comment, I do strongly recommend you to use compositional data analysis, because correlation when you're working with closed data, will generate spurious correlation. It will not work as good as it should. And when you use compositional data analysis, you will get the perfect, the best, the real correlations from your data. So thank you very much for your attention. This is my coordinates. Again, that's the book that you can buy on Amazon. And if you have any questions, please, I'm here to answer them. Again, thank you very much for your attention.
Спасибо большое, Рикардо. Ну, вопросы, может, есть в зале? У нас есть, да, есть? Где?
Скажите, пожалуйста, вот вы говорили о том, что надо использовать те данные, у которых максимальная коллинеарность. Ой, извиняюсь, максимальная коэффициент корреляции. А рассматривали ли вы в этом случае влияние мультиколлинеарности, которые как раз ухудшают качество модели? Спасибо.
Yes. I show you a very simple example just to, I mean, if I will use a real life case, it would be very complicated to explain it, okay? But yes, the multilinear or the multi-correlation or the multiple adjustment that you can do to your data, that will help with your normal method. But why waste time with that? If you use compositional data analysis, you will jump that need. It will just present your data in a way that will only respond to the true correlations. And when you do, if you have really a multi-correlation type of deposit, you will get 2 or 3 different RCCs, and each one of them will map specifically one target. That is the beauty of the RCC method.
Последний вопрос. Еще подскажите, пожалуйста, рассматривали ли вы возможность подобного анализа алгоритмами машинного обучения? Потому что там также рассчитывается расстояние и так далее.
Okay, yes. There is a big difference. And this book that I mentioned here is actually, it contains compositional data analysis and machine learning, and also one thing called insight. Okay, there is a big difference with the form that artificial intelligence and machine learning process data compared to what statistic does. You need a lot of data for machine learning to work properly. And the way they work, the way the machine learning works is completely different from the way the statistic way works. You mentioned correctly that it measures distances, okay? But these are not correlation distances. This is a different type of heuristic distances. So yes, you can use artificial intelligence. In the case of artificial intelligence, the more data, the better. But this is not what we usually have in the field when we are looking for our next gold deposit or our next oil and gas deposit. So I have used machine learning with my compositional data analysis. And again, it's just an overkill, because usually with just the compositional data analysis, I get such good results that allow me to, put the drill here, and I will intersect the mineralization. But again, machine learning and artificial intelligence is also very useful, but it's not the subject of this conversation.
Рикардо, извините, пожалуйста, еще один вопрос. Вот все-таки четче определение открытости и закрытости данных. Открытые данные и закрытые. Вот более конкретные примеры.
Okay, anything that is estimated over a total sum is closed. For example, everything in geochemistry, part per million, part per trillion, percentage, all geochemical data is closed. Geophysical data, almost all geophysical data is open. For example, the magnetic field can go from plus whatever to minus whatever. There are not limits. But in geochemistry, you can only go from 0 to 100%. So that is what is called closed data. Days of the week, there can only be 7. Okay, so that is a closed data. Now, you can use compositional data analysis with open data too. It's not a problem. It's a method that you can apply for closed data and open data. But it was designed originally for closed data. I hope that you understand now what is closed data.
Как трансформировать дни недели в открытые данные?
Sorry?
Как трансформировать дни недели в открытые данные?
That you use the ALR, CLR, or ELR. There are 3 algorithms in the program. It's called COLAPAC.
И что ж тогда будет? Не 7 дней недели, а что это будет?
No, the thing is that the sum of the 7 дней недели не будет 7, будет 0 или будет какой другой номер. Понимаешь? Okay, let me try to explain this thing. If you have a Firstman, okay, muy любимый geochemist. Firstman has a law that if you take a sample and if you have the possibility of doing the best analysis ever, you can find all the composition, all the elements in that sample, and the sum of all those elements will be 100%. That is a law. Okay. Now, so when we do an analysis, we are assuming that the total sum, the total content, can be only 100% or less. So when you apply the ALR, the algorithm, the central log ratio, the additive log ratio, the integral log ratio, what you do is you transform this data so the general sum will not be 100%. It will be or 0. So you convert, for example, instead of, let's say, Monday to Sunday, it will be 1, 2, 3, 4, 5, 6, and 7. So instead of having 1, 2, 3, 4, you will have -3, +2, 5, -10, and the sum of all those will not be 7, will be 0. That is how the system transform the data, converted from a closed system into an open system. Once the system is open, you can use Excel, you can use the normal method of statistics that you know. But if your data is closed and you try to use correlation, regression, even principal component analysis, you will be working with the real thing, but you will also generate a series of spurious correlation, and that will take down the effectiveness of your results.
Спасибо.
Again, it's very difficult in just an hour try to explain all the things. This is a new branch of statistics. There is a link in the presentation for, I mean, you just Google CODA PAC or CODA work. you will get to the site. There is a site in the internet with plenty of geological white papers, you know, of papers explaining all these things, etc., etc. And I hope that we can organize, as I said, a more serious course, because in my opinion, really, compositional data analysis should be taught at every university that trains geologists, because it's amazing that we get out and we don't know about this. And everybody uses correlation because it's the most strongest method available to us. But now we can use it in the proper way.
Спасибо большое, Рикардо. Было очень интересно. Давайте, наверное, поблагодарим Рикардо за выступление. Но я хочу, да, поддержать его слова, сказать, что сейчас мы разговариваем, ну, ведем переговоры, как организовать этот курс, вернее, как его представить лучше. И, скорее всего, на платформе геовебинары этот курс пройдет на платформе, но вот, может, с Владимиром Александровичем тоже перемолвили, что, может быть, такой курс.
Если честно, вроде бы действительно наш курс математической статистики для геологов очень усеченный. Там, в общем-то, корреляционному анализу посвящено не так и много. Ну, действительно, какое-то ломкое сознание, то есть происходит. Вот то, что сейчас я услышал. Сначала мне показалось, что что-то, так сказать, в начале лекции немножко как бы что-то тут примитивно. А сейчас я понимаю, что да, тут что-то действительно есть, и над этим надо задумываться. Вот сейчас мы столкнулись, например, в обработке Аксуга, 40 элементов количественного анализа плюс полный силикатный анализ и огромные статистические базы. Да, мы используем факторный анализ, но действительно с слабыми корреляционными связями надо возиться, надо смотреть. Появляются новые ассоциации, которыми надо разбираться. И вот я думаю, что даже нашим преподавателям стоит, так сказать, задуматься и посмотреть, вот именно что это такое открытые, закрытые данные, как это идет, происходит трансформация и что мы из этого можем взять. Потому что, ну и честно, в нашей классической геологической математической статистике эти подходы не рассматриваются. Я думаю, нам стоит задуматься. Спасибо большое, очень было интересно.
Спасибо вам.
Спасибо большое, Рикардо. Спасибо, кто слушал нас онлайн, из интернета. Спасибо всем, кто сегодня в зале. И спасибо форуму Мингео, что организовал и провел этот мастер-класс. Рикардо, до новых встреч.
До новых встреч. Спасибо большое. Пока.